Hi everyone, my name is Tom Porcheto and this is a presentation for designing a single-stage rocket to orbit to be launched to the International Space Station. So I assume that you're expecting a boring and classical presentation of which combustion energy engine of SpaceX should I choose to design this rocket and which chemical propellant is going to be the most effective. But this presentation will be more exciting because my rocket design is based on a nuclear thermal rocket, which uses a solid core fission reactor. I chose to design the rocket with this feature because based on my research, this technology is at least 2 times better than any combustion engine in terms of specific impulse, which is the total impulse or total change in momentum produced per unit of propellant consumed. And NTR design reduces the mass ratio by a factor of 4.5 plus at least. Throughout this presentation, you will find out why this technology, I think, will revolutionize aerospace engineering in the next 20 to 30 years. So there are many considerations to take into account that will be included in calculations and analysis shown in the next slides, but the most important considerations here are the 10,000 kilogram payload that the rocket has and the fixed 400 kilometers distance of the ISS, given that the ISS orbits at an altitude between 370 to 460 kilometers. So the most important assumptions made to take into account are the propulsion, which is the propulsion approach. In this case, it's the nuclear thermal rocket. The specific impulse, which for an NTR can be 900 seconds. Essentially, a higher specific impulse means the engine can generate more thrust for a given amount of fuel, making it more efficient. And another important fact is the velocity of exhaust for an NTR. And the dry mass, which is basically the hardware of the rocket. Here we have more assumptions based on the research made with values that will appear in calculations. Here we have some simplifications to make the calculations more straightforward. So here is a free body diagram of our rocket, but considering that we will have a perfect launch from the equator, we end up having zero aerodynamic lift force. These calculations of kinetic and gravitational potential energy per kilogram, so joules per kilogram, help to understand propulsion efficiency and fuel requirements, and also required thrust. So we calculate the drag, which steals part of the delta velocity. So this means that the rocket requires extra fuel, which is exponentially costly, well, due to the rocket equation. In this case, it is important to note that the resistive force calculation is proportional to velocity squared. So applying the formula for resistive force yields 100,000 newtons. So considering the air density, the role that air density plays, it's so an important role is an influential role is up to 100 kilometers of altitude. So we calculate the work from 0 to 100 kilometers to be 10 billion newtons meter. So total energy requirements, here we have the final result for 341 billion joules for the lift of the rocket and the 10 tons payload. And in terms of delta V, which is the total velocity change required to deliver the 10,000 kilograms to the low Earth orbit, we obtain 9.31 kilometers per second. So now I will dive more deeply into the selection of an NTR. So a solid core nuclear thermal rocket uses a fission reactor to heat a propellant, which in this case will be hydrogen, to generate thrust for spacecraft propulsion. To be more specific, the core of the reactor, which has uranium-235 as its fuel, heats the propellant, and the hydrogen flows through the uranium fuel reactor channels, heating to 2700 plus Kelvin, and is then expelled through the nozzle to produce thrust. So, for example, for the same mission to Mars, NTRs could deliver 2 to 3 times more payload than chemical rockets. It can also do the mission 3 times faster, from 9 months to 3 months. So here we have the specific impulse formula and important values using the rocket equation. So the exhaust energy yields 37 million joules per kilogram for the NTR. So here you can see efficiency comparisons between the current most accepted propellant used for combustion engines and the 90% efficiency of the solid core fission reactor. So for illustrative purposes, here we can see the diagrams of a combustion engine, and to the left and to the right the NTR engine. So this is one of the most important calculations, which is the mass ratio derived from the Tsiolkovsky equation, aka the rocket equation, which refers to the proportion of a rocket's mass that is dedicated to fuel versus the mass of the rocket itself. So for the NTR, we obtained 2.87. So we can see a reduction by a factor of 2.8 for the mass ratio and 3.5 for initial mass compared to a combustion engine. So here, this is a graph that shows that at 2.87 mass ratio, we obtain a really payload efficient single stage to orbit rocket. So therefore, we can say that the mission is achievable with the presented design of the rocket. So going into the analysis of the results, so we can see that the NTR, the SSTO NTR, achieves the required delta velocity of the 9.31 kilometers per second, with a mass ratio of only 2.87 to 1. So yielding also an initial mass of 49.9 tons, composed of 32.5 tons of propellant and 17.4 tons of dry mass and payload. So over 1/3 of liftoff mass remains available for non-propellant systems. So with a 10 tons payload, the SSTO's payload fraction is 20%. So that's like a dramatic improvement over the chemical SSTOs, which are between 5 to 6%. So furthermore, the most important fact to note is that the NTRs convert between like 80 to 90% of reactor heat into propellant kinetic energy. So at a velocity of exhaust of 8.83 kilometers per second that we assumed, so each kilogram of hydrogen yields 39 megajoules of exhaust kinetic energy. So this efficiency directly translates into smaller propellant loads and vehicle size. So here I leave you with a comparison that you can see after the presentation, and here are the sources which I used to make the presentation. Thank you very much.